Today I want to share my experience using HashiCorp Vault to manage secrets in a development environment. I'll also cover some best practices for web application development. I think these are great tips for anyone interested in web development. First, please check if Windows Subsystem for Linux, WSL, is enabled on your computer. I'll just call it WSL. Mine has been enabled for a long time since I have Docker installed. You should update your current WSL version to the latest one. To do this, use the command WSL update, and then use WSL version to check that the update worked. Open your Windows terminal and type the command WSL install dubuntu 24.04. This will install a brand new Ubuntu Linux distribution if you don't already have one set up with WSL. You can find all the related commands on my GitHub page, and you can download this video to follow along and do it yourself. Once the Ubuntu Linux download and installation are finished, you will be prompted to create a default username and password. Please be patient while I explain the initial steps. My speaking might jump around a bit at first. Type sudo su to gain root access. You will need to type the password you set up initially to confirm this. The next step will allow you to use sudo without needing a password in the future. To do this, simply create a file in the etc. sudoers d folder. Use the command from my GitHub page and change the username to your own. Now, press Ctrl+D to log out, and then type sudo su to log in as root again. You'll notice that no password is needed this time. Since this environment is just running on your own machine for development, this simple change will save you a lot of time during future development work. Next, we will use the apt install command to install necessary packages like SSH and unzip. I think this part is straightforward, so I will skip ahead past the installation and apt upgrade process. I will also show you an example of using PuTTY to log into your WSL while keeping the Windows terminal open. Next, please visit the link provided on my GitHub page to download the password vault from the official website. Important. Make sure you download the appropriate version for your CPU, e.g., x86, ARM, or macOS. Use the wget command, along with the web link from the official page, to start the download. Now, use the unzip tool, which we installed earlier, to extract the downloaded file. Next, move the Vault executable file by typing mv-vault usr local bin. This step allows all users on your system to run the command. Finally, check that it works by typing vault version. If it fails, you most likely downloaded the wrong binary version. Now, use the command available on my GitHub page to create a Vault user. This user is specifically for the process that will be running the daemon. Now, use the commands from my GitHub to create the necessary folders for Vault, one for system settings and one for data storage. You then need to change the folder permissions so that the Vault user owns them. This ensures the daemon can run correctly. Finally, set the permissions to 750 to prevent unauthorized access by others. Next, you need to copy the settings file, named vaultlink.hcl, from my GitHub. This file defines key settings, like the Vault data file storage location and the IP addresses that are allowed to connect. For security, I recommend setting it to listen only locally and enabling disable_mlock to prevent sensitive data from being written to swap space. Now, copy the Vault service file from my GitHub into the directory, etc. systemd system. This will let you enable Vault to start up automatically when your system boots. Later on, I'll guide you through unsealing the system using the Oracle Cloud Key Management System. Paste the script from my GitHub. This script does three things. It sets environment variables in your bashik. It enables the Vault service for startup, and then it starts and checks the service status. If the status shows up and running and enabled, that means Vault is ready to start automatically with Linux. Following that, use the command from my GitHub to initialize the Vault service. Be sure to copy and save the root token and the 5 unseal keys in a secure location. Next, I'll log into my Oracle Cloud environment, which I created 3 years ago. Oracle Cloud offers a fantastic, always free service for developers. Unfortunately, I chose the UK West region, which only allows one domain. If you choose the UK London region, you can create 3 domains. Today, I'm using a workaround. I'll simulate a new domain by creating a compartment, which lets us organize resources as if they were in a new domain. If you have your own account, I strongly recommend that the default domain is sufficient for creating your API account. I want to give you some background on why we're using Oracle Cloud Vault to unseal our local vault. By default, HashiCorp Vault seals itself every time the service restarts. This means you have to manually unseal it. Oracle Cloud Vault is a more secure and always-on system that automatically unseals our local vault when our server restarts. To make this work, the admin user needs API access rights to the service created in Oracle Cloud Vault. That is why I am introducing this service. When creating the domain, remember to select the free tier. For your reference, I'm using my own email address as the administrator email. This new administrator user is only for the purpose of creating the API private and public key pair and the OCI configuration file. This process may take some time. After the domain is created, follow my screen and navigate to the Administrator tab, then click on my name on the administration page. Although my screen might not be perfectly clear here, I hope you can follow along. On the next screen, you will find API keys. Click the Add API Key button to generate a new key and download the private and public PEM files directly into your WSL environment. This whole process will also generate a configuration file, which you must copy to a safe location. Note that I need to hide my tenancy ID for security, and all the other files will be deleted after this video is made. Next, we will create the Oracle Vault to securely store the unseal keys we copied earlier. From the main menu, you can simply type Vault to go directly to the Vault section, Key Management and Secret Management. In this area, you can create your own Vault key. The key name is completely up to you and won't affect my script. All you need to remember is to use its unique OCI. As shown on the screen, be sure to create a master key and select plain text when you create the secret. In the Create Key window, manually select HSM mode and keep the default encryption settings shown on the screen. Remember, the key name is entirely up to you. When you move on to create the secret, make sure you select the appropriate key for the encryption process. In the Create Secret window, remember to select Manual Secret Generation. This option allows you to paste the generated unseal key in plain text. By default, this key will be encrypted, but you will still be able to view its original content later. I will skip the repetitive key creation steps here. To update the content later, you can select Create a new version. Finally, I recommend you enter at least 3 unseal keys into the key management system. It's up to you if you want to include the root token as well. Our script will only use the secret's unique OCID to identify the unseal key. Next, open a Windows terminal to begin creating the unseal daemon. First, copy the script from my GitHub to create the FastApi user. This user is specifically meant to run the daemon. It's always best practice to run daemons as a non-root user, even though this environment is not publicly accessible. The script is written in Python and uses the OCI library. It also leverages UV package management, which is extremely fast and simplifies Python version control. UV handles the Python environment if a version file exists in the folder. Please bear with me, as I missed recording the video on how to install UV, but the instructions are also available on my GitHub. You might find it strange that I'm changing the user's shell from nlogin to bash. This is actually a way to simulate a production environment, which should strictly use nlogin for safety. However, I temporarily need bash so I can set up the UV environment under the FastApi user. Once the setup is complete and the service is running, I will change the shell back to nlogin. I also manually created the necessary folders, which I admit is not the best practice. I'd be happy to discuss better solutions to achieve this setup. I will now use su to switch to the FastApi user and get everything working. After that, I will edit the file to change the default user to FastApi. This is necessary for remote debugging from VS Code on Windows. To prepare the script, I will create a Git directory and clone all the code from GitHub into it. The specific path is flexible. Just make sure you update the paths in both my script and the service file if you choose a different location. After you clone my public script from GitHub, use uvsync. This command will immediately download the required Python version, based on the version file, and install all necessary packages to make the service run correctly. The service's main job is to unseal the password vault automatically. It is a best practice to never store any unseal information directly on your server, which ensures the passwords kept in the vault remain secure. The next step is to create the link to .ochi folder and then copy the config file generated from Oracle Cloud into it. You can either copy the entire config file from Oracle, or you can paste the information line by line into my example config. I recommend just pasting the entire content from Oracle Cloud. After that, you only need to put the correct path to the private key into that config file. You can use the WSL's default mount feature to easily copy files from your local C or D drives. Finally, remember to use chmod 600 to set the permissions, which prevents others from reading the file. As you can see on the screen, mount D refers to your D drive on the host machine, and mount C refers to the C drive. I've already renamed the private and public PEM files to make them easier to manage. I've now found the text file I saved locally and I'm pasting the content into Nano. For security reasons, I'm hiding my tenancy ID, but all the other information can be seen. All you need to do here is enter the full path to your PEM file. Once that's done, we'll be ready to run the unseal script to test if it works. Before starting the script, you must modify the link to .env file. You need to copy the tenancy ID and the OC IDs of at least 3 unseal keys into it, as shown on the screen. Once updated, my script can successfully fetch the unseal content from Oracle Cloud. I'm only copying one example here, but the others should work similarly on your system. When you run the command uvrun link to main.py, a return code of 0 means the unsealing process was successful. My final service is set up to run this Python script right after the Vault service starts, meaning every restart will be unsealed automatically. I'll check the current status using Vault status. I apologize that I forgot to capture the systemctl enable command in the video, but I will make sure to add it back to the GitHub instructions. This concludes the setup, and our final step shows the automatic unsealing after the service restarts. Now, I'll show you a very short script written in Python to read secrets from the password vault. As we know, you can use curl to access the content, so any language can retrieve the data correctly. The main thing is using the right path and the correct token. The script requires almost no special components. I'm skipping the root token login screen in the interface because the service is running locally on port 8200. By default, you can log in and perform all actions with root privileges here. As the screen shows, we can retrieve the updated content from the vault immediately after a new version is created. Now, we need to move on to creating an access control list, ACL, and an operation token. The root token should only be used in emergencies. I strongly suggest creating a read-only token for the application we write to access the vault secrets. The first step is to create the ACL and define the data and metadata paths, as shown on the screen. Afterward, we'll create the proper operation token, setting an appropriate time to live, TTL. We can then renew this token regularly. After completing the script that generates a token based on the ACL, this token is now safe to use in your application to properly retrieve secrets. Be careful when copying the token, as it may be longer than the root token. Remember, never use the root token in your application for security reasons. Next, I'll briefly discuss a real application where I use the password vault. The laptop I'm using is just for this demo, and it took some time to initialize this development environment, including setting up an API gateway. I believe the password vault is excellent when working with webhooks to decouple source code from system settings. In production, I secure the password vault login with VPN protection and Radius plus Google Authenticator. I feel this offers strong protection against hackers. I'm now demonstrating an application that runs across various environments. By storing all settings in the vault, the source code for production, UAT, and development is identical. This means we can rotate API keys and passwords on a schedule without ever touching the source code, unless there's a logical change. I'm using a free API gateway for the webhook example, which is useful for debugging. In this real-world example, I'm updating the Square notification URL to a randomly generated URL from a free API gateway. Since this URL may need regular updates, this is a perfect test case. I also need to update the corresponding setting in the merchant console in the sandbox environment. For all the systems I maintain, I separate production, development, and UAT databases. I do this to make it easy to test all special cases. As shown in the free API log, the 200 status code means the communication from the merchant to our local backend was successful. I'm going to show you how I use Wireguard VPN and website IP blocking together to protect my system. Right now, I am connected to the VPN, and my external IP address is the same as the server's IP. When I disconnect the VPN, I use curl to a standard IP check site, and you'll see I have a different external IP. When I try to access the browser again, I cannot connect to the system. When I reconnect the VPN, I can successfully retrieve the server's IP address and access the Vault UI again. Now, let's test the full system using the API gateway and the payment gateway sandbox. The FastApi code runs in WSL, simulating the production server, while the Angular front-end can be debugged in the Windows environment. This allows us to debug both front-end and back-end code simultaneously. The webhook uses the standard Square code to decode the postback body and validate it against the signature provided by the merchant console. This setup allows us to test all webhook functionality locally, eliminating the need to push to staging or UAT environments for remote debugging. First, let's complete the normal workflow to test the webhook. For standard JWT bearer token authentication, the proper way to secure the refresh token is by saving it in an SSL secured cookie in the browser. For browser-only REST API applications, using SSL secured cookies is the best choice. As you see on the screen, my system generates a payment link, and I'm using it to complete a test payment in the sandbox. The webhook is set up to receive the successful payment notification from the merchant and then update our system's data record. Because this testing is performed locally, I'm using a free API gateway to help redirect the merchant's response. If my FastApi application successfully receives the payment confirmation, it means all our systems and settings are working perfectly. As you can see on the screen, the returned content passed the signature validation. This successful validation is precisely why I had to update the notification link, to ensure the verification process works correctly. As highlighted in the network function of the dev console, the set cookie header is sent directly from the backend to the browser. This cookie contains the refresh token and is secured with HTTP only, which prevents front-end JavaScript from accessing it, and secure, which ensures it's only sent over HTTPS. The rest of the response only contains the access token, which is stored in memory only, avoiding conventional storage like session storage or local storage for sensitive session data. Since the refresh token is the key to recovery, the session will be lost if you manually delete that refresh token. Here, I'll demonstrate. If I delete the SSL secured cookie, the login session is immediately gone. If the user refreshes the browser, the system will lose the entire login session and prompt the user to log in again. This happens because the access token is stored only in memory, and the system cannot locate the refresh token, which is what keeps the session alive. Remember, REST APIs are stateless and rely entirely on these tokens to maintain the session state. Let's continue with the login process. I learned from the Shopify workflow. For new registrations, they send an OTP, one-time password, to ensure the email is valid. Now, I'm copying my password from another screen and pasting it in to log into the system. After logging in, the response only includes the access token, which is set to expire in 15 minutes. The system is designed to refresh this token every 13 minutes using the persistent refresh token. Because sensitive login information is not saved in conventional storage, like cookies, local storage, or session storage, a typical JavaScript hack will find it difficult to steal credentials. Following the practice of many large tech companies, we keep the refresh token's expiry period long, often a couple of days, to allow the user to conveniently retain their session. This method is secure because we rely on recognizing the machine or IP information. Users can refresh the browser or even close and reopen the browser, and the existing refresh token will safely restore the session.